Now let's talk about factors affecting solubility. And this is what we'll use as kind of a first approximation to kind of justify what would happen, and we'll be able to use this to predict whether or not something is soluble in something else. So the energy cost in breaking intermolecular forces or bonds in the reactants must be paid back in the new attractions in the products to be energetically favorable. So we need to analyze what types of intermolecular forces we're going to see, changing here. So breaking a strong interaction like hydrogen bonding to form a weak interaction such as London dispersion forces is not energetically favorable. So typically we use this saying that says like dissolve like, because only similar forces are comparable in energy. So if we look at something like water, and if we mix this with hexane, the question is, would hexane form an aqueous solution, or would this hexane dissolve in water? If we look at water, the intermolecular forces that are present are hydrogen bonding, dipole-dipole interaction, and London dispersion forces. In hexane, the only intermolecular forces we have here are London dispersion forces. And in the hexane solution, we would also have London dispersion forces as our only intermolecular force of attraction. So this is like trying to mix oil and water. Okay, hexane will not dissolve in water because the London dispersion interactions between the water and the hexane don't really exist very well. And these London dispersion forces are weaker than the water-water intermolecular forces, which has the hydrogen bonding here. So it would not be energetically favorable for this particular reaction to take place. Okay, so therefore we won't get this to dissolve, and if we would mix these two solutions together, we would get a water layer and a hexane layer, and we would see two distinct layers. On the other hand, if we took water and we added that to sodium chloride, would we get an NaCl aqueous solution? So here in the water, we have, again, hydrogen bonding, dipole-dipole, and London dispersion forces. In an NaCl solution, we have ionic bonding going on here. When we would form this solution, we would get an ion-dipole interaction. So when this typically happens when a salt dissolves in water, the ions are surrounded by many water molecules, somewhere along the lines of around 10 to 30, depending on the size of each of these ions. So even though we have this strong attraction of hydrogen bonding in the water, we can reason our way through this saying that the ion dipole interactions are roughly as strong as the ionic bond. So what we would see here is we would see a solution where we populate that solution with cations and anions, and we have water completely surrounding them. There's a figure in your textbook that really emphasizes what's going on in this particular case here. So one of the things that we can kind of mention from this, and a key takeaway message from looking at all of this, is that the stronger the interactions are between solute and solvent molecules, the greater the solubility. And from this, we can say that polar liquids dissolve in polar solvents, and nonpolar liquids dissolve in nonpolar solvents. And again, this is going along with the saying of like dissolve like. And we need to make sure that each of these reactions are energetically favorable. So we'll be looking a lot at the delta H of all of these, substances that are, all the species that are present in each of these solutions.